Hi, everybody, and welcome to today's session of the Spectral Geometry in the Cloud seminar. Today, we have Peter McGrath, who will talk to us about Immersed free boundary Annuli in the Unit 3 ball. As usual, if you have questions during the talk, don't hesitate to unmute yourself and ask them. Peter, the floor is yours.
Okay, thank you. And I'd like to thank the organizers for the invitation. As was just mentioned, yeah, please do ask if you have questions. On some seminars I've been in, people put questions in the chat. I may or may not be able to see those very quickly, so don't be shy. So I'd like to talk.
We'll try to relay questions in the chat if they are there.
Yeah, that would be helpful. So thanks. So this is some work I did recently with Nikos Kapouleas at Brown. See. So I'd like to begin with just some definitions. So certainly some of the spectral geometers here will be familiar with free boundary minimal surfaces, but I wasn't sure if everyone would. So for the majority of this talk, I'll be talking about submanifolds of an ambient manifold M that are minimal, their mean curvature vanishes, and they meet the boundary of M, which I assume to be smooth here. I assume everything to be smooth, orthogonally. So such surfaces are called free boundary minimal surfaces or free boundary minimal submanifolds, if you like. And sometimes I'll use the abbreviation FBMS as some people do. So how or where do these arise geometrically or variationally? What is the purpose of these two conditions? So the purpose is that an alternative definition is that these objects are critical points for their k-dimensional area or k-dimensional volume. And so this can be seen from the first variation formula, standard differential geometric calculation. So if you have a one parameter family of immersions, sigma t, where sigma 0 is your original sigma, so you deform your sigma slightly, and then you decide to take the derivative of the k-dimensional area, which I denote like this. Standard calculations shows that you get two terms. One term is an interior term, the other term is a boundary term, and the interior term is the integral of the inner product of the variation field with the mean curvature. So H here is the vector valued mean curvature. And your boundary term is the dot product of your variation field with the outward pointing normal. And so if you'd like this, if you're searching for the critical points for this volume function, you want this always to be 0 independently of your x. And it's not difficult to show that this can only happen if your mean curvature is identically 0, so the minimal condition here. And then if this inner product is always 0, which means that your sigma meets the boundary orthogonally. So you have these two geometric conditions. So for the rest of the talk, the geometric objects I'll be interested in are these free boundary minimal submanifolds. And really, for this talk, we'll only be interested in the case where the ambient manifold is the three-dimensional Euclidean ball in the usual R3. Okay, so I like to go through the very, very simplest examples. And so the first trivial example is the equatorial disk or any equatorial disk. So this is a disk that passes through the origin, and so it's totally geodesic, so it's clearly minimal, and then it's geometrically obvious that it meets the boundary orthogonally. So you can certainly slide these disks up so they no longer pass through the origin, they remain minimal, but then they don't meet the boundary orthogonally. And there's a rather beautiful theorem that says that these trivial examples are really the only examples in their topological class. So among all immersed free boundary minimal disks, so just up to their topology, genus 0 and 1 boundary component, the only ones, even in general codimension, are these flat equatorial disks. So I put two sets of authors here. So Nietzsche did this in the 80s when n was 3, and Fraser Shane did this for a general n. So the method of this proof is it's basically a Hopf differential complex analytic proof. So I'd like to go to the next trivial example. So if you take a Euclidean catenoid, and if it passes through the origin, there's one particular scaling of it. So if you scale a minimal surface in Euclidean space, it remains minimal. And there's a particular scaling of the Euclidean catenoid that has this orthogonality of the boundary condition, a unique scaling. And of course, as with the disk, you can rotate this annulus, and so it still satisfies the condition. And so this is called what's called the critical catenoid. And as usual, I'm abusing notation slightly by identifying this object in any of its isometric images under rotations or reflections, just as we did for the disk. So there's an important conjecture that claims that this object is the only, just as we had a uniqueness result for the equatorial disk. The claim is that this critical catenoid is the unique embedded free boundary minimal annulus, again, up to the obvious isometries. So in a somewhat confusing introduction of one of his papers, Nietzsche claims that this conjecture is true. So I won't read to you exactly what he says here, but as I interpret what he says here in the introduction of one of his papers, just asserts without proof that this catenoid is the only ring type annulus in the ball. So the conjecture, as stated up here, is still open. It is known to hold with some additional hypotheses. So for example, if one assumes that the first Steklov eigenvalue on the annulus is 1, then the conclusion, the rigidity, is known to hold. It's also known if one assumes some discrete reflection symmetry, so reflection symmetry through the 3 coordinate planes. Somewhat more recently, with Rob Kussner, we were able to improve this previous result slightly to just an order 2 antipodal symmetry. So there's some partial progress on this conjecture in general, with some additional assumptions. So a natural and obvious question in the statement here versus the statement of the Nietzsche-Fraser-Shane theorem for the disk on the previous slide is the question about embeddedness here. So the previous theorem was true for immersed disks, and some recent work with myself and Nikos and this other group of 3 authors shows that the embeddedness really is necessary for the annulus case. So if you go to immersed annuli, there are infinitely many non-congruent examples of non-rotational free boundary annuli in the ball. And when I say non-rotational here, I mean not coverings of the critical catenoid. So clearly, if you just take a covering of the critical catenoid, that's immersed and non-embedded, but that's sort of a trivial example. So this is what I'd like to discuss in some detail in the rest of the talk. But before I get to the actual construction, I'd like to discuss a little bit some more properties and questions in the relation between the study of free boundary minimal surfaces and the Steklov eigenvalue problem. So here is an image, a beautiful picture produced by Mario. So if you're here in the talk and you haven't seen Mario's gallery of free boundary minimal surfaces, you should definitely look. I think earlier I saw Mario's name in the audience. So he's put a lot of work into this, and this is a picture of computer rendering of one of these free boundary immersed annuli. So I'll get a little bit later in the talk to describe. Obviously, you can see there are some symmetries here, so I'll discuss that in a little bit more detail later. But in short, these can look quite complicated. So another question in a different direction is, if you start looking in more complicated settings, so not just genus 0, 1 boundary component, genus 0, 2 boundary components, that you can ask general questions about whether there exists a embedded or immersed free boundary minimal surface with prescribed number of boundary components, prescribed genus. There's been a huge amount of progress, huge amount of work in general on these types of constructions with various different methods, including eigenvalue optimization, gluing methods, min-max techniques. I would not be able to do justice to all this work in general in this talk. So I'm just not going to mention very much about that in general and try to focus just a little bit on what we know for genus zero surfaces. So I'll just tell you a little bit about what the status is there, what's known, just to paint a little bit of a picture to give some context for these immersed annuli. So there were some constructions by gluing of doublings of the equatorial disk. I'll show a picture in just a moment. And more recently, there have been some constructions by several authors, including some of the organizers of this seminar, of examples of genus zero, embedded examples of genus zero surfaces that are sort of in a limit appropriately very close. The varifold limit converge to the boundary of the three ball. So I have some pictures, again, courtesy of Mario. So this is a picture of a doubling of the disk. So what you can see is you could see basically essentially two copies of the disk, and then they're connected by approximately half catenoidal, pretty small half catenoidal annuli. And there's a discrete one parameter family of these surfaces where in a dihedrally symmetric way, you put more and more of these half catenoidal annuli that get smaller and smaller in their number. And as the number of these half catenoidal annuli gets larger, their size gets smaller, and then the two sheets of the two copies of the disks get closer and closer. So the varifold limit is simply two equatorial disks. So on the other hand, there are these examples that are close to the boundary. So this is one that has icosahedral symmetry, or at least approximately icosahedral symmetry. And then, as I mentioned, there are at least three sets of authors who have studied examples like this pretty recently. So these last two slides showed some embedded examples. So I'd like to talk a little bit about some connection between free boundary minimal surfaces and the Steklov eigenvalue problem. So probably as everyone here knows, the Steklov eigenvalue problem can be posed on a compact Riemannian manifold. You look for harmonic functions in the interior that have this boundary condition where the normal derivative is proportional to the function along the boundary, and the sigma in this notation is called the eigenvalue, the Steklov eigenvalue, U is called the eigenfunction. And there's a discrete spectrum, so 0 is the smallest eigenvalue corresponding to the constant functions. And then you have the higher eigenvalues, and the first non-zero eigenvalue, sigma 1, is important for this talk. And the simplest connection between the general Steklov eigenvalue problem, which you can state intrinsically for surfaces, and actual free boundary minimal surfaces embedded or immersed in the ball, is that the ambient coordinate functions on the Euclidean space, on Euclidean 3 space, the restrictions to your FBMS are actually Steklov eigenfunctions with eigenvalue 1. So checking this is essentially a triviality, but this is the beginning of a very strong and important and not completely well understood link between the intrinsic Steklov eigenvalue problem and the free boundary minimal surfaces. So I'd like to discuss a little bit of what's known about Steklov eigenvalue bounds for surfaces, genus zero surfaces almost exclusively, and then area bounds for minimal surfaces, again contrasting what's known for the embedded case and the immersed case. So there's a general bound for a genus zero Riemannian surface, not necessarily a free boundary minimal surface due to Kokorev, which says that the normalized first eigenvalue, which is gotten by taking the actual first eigenvalue and making a scale invariant quantity by multiplying by the boundary length, this is strictly less than 8 pi. And so in some important recent work, it was shown that one can construct families of embedded genus, there's a typo there that should be genus 0, of course. Genus 0 free boundary minimal surfaces that actually saturate this bound. So those surfaces happen to have their first Steklov eigenvalue equal to 1, and they look, roughly speaking, like this. Let me switch directions slightly and mention an important conjecture, which is analogous to Yao's eigenvalue conjecture for closed minimal hypersurfaces, embedded minimal hypersurfaces in the spheres. So this conjecture was stated by Fraser-Lee approximately 10 years ago. And the version I state here is for free boundary minimal surfaces in the 3-ball. So for hypersurfaces, embedded is crucial here. And the claim is that the first Steklov eigenvalue on such a thing is always 1. So we know from the previous slide that the coordinate functions are Steklov eigenvalues with eigenfunctions with eigenvalue 1, and the claim is that they are the first eigenfunction. So 1 is indeed the first eigenvalue. So this conjecture has a lot of very strong consequences. I will mention a couple of them here. So a trivial calculation that has nothing to do in its proof with this conjecture is that for any free boundary minimal surface, whether embedded or not, its boundary length is twice its area. And so you can basically convert statements that have to do with scale invariant eigenvalue bound. You can convert this length to area, essentially. And so if you chain a couple of these things together, if you suppose that this conjecture is true, and then you use this fact, it means that for any embedded genus 0 FBMS in the 3-ball, its area is strictly less than 4 pi. So this would be a consequence of this conjecture here. For example, another consequence of this conjecture, if you believe the conjecture to be true, is in fact the uniqueness of the critical catenoid. So if you knew that this conjecture were true, you would know that the conjecture about the uniqueness of the critical catenoid in the embedded case I mentioned before, that would also be true. So this eigenvalue conjecture is believed to be difficult. The best known progress in general for this conjecture is that you can always prove the conjecture up to a factor of 2, so that the first Steklov eigenvalue is at least a half. So recently with Jacobi Zhu, we showed that this area bound for embedded genus 0 FBMS is true independently of the conjecture. So we were able to just check that the bound is true by combining a couple of other known facts from the literature and a calibration type argument. So most of the things on this slide I mentioned are, except for this theorem up here, are for embedded FBMS. So I wanted to give some sense for some rigidity and some structure theorems for such things, because the immersed annuli that have been recently constructed basically show that all of these area bounds that are true in the embedded case are just not true. So now I want to switch gears and talk actually about the constructions that we do for the immersed annuli. And I want to begin with a very useful analogy to the Delaunay surfaces. If you're not familiar with them, they are constant mean curvature annuli in R3. So they were discovered by Delaunay at least going back to the 1860s. It's possible other people had discovered them earlier. So there are one parameter family of rotationally symmetric periodic annuli in R3. And you can think of them as interpolating between a cylinder and a necklace of spheres. So there's a singular limit where the family degenerates into a bunch of spheres put end to end, just kissing or touching along a sequence of diameters. In truth, the family can be extended further to immersed surfaces, but I'm not going to talk about those at all. So there's this one parameter family of embedded CMC surfaces that are rotationally symmetric, singly periodic, and interpolate between the cylinder and this necklace of spheres. And so this is kind of a motivating principle for an analogy between these objects and the one parameter family of moduli of immersed free boundary annuli that we expect. So we expect a similar moduli space, a one parameter space of immersions, free boundary minimal immersions of complete strips. And in this analogy, the cylinder for the Delaunay surfaces gets replaced with the universal cover of the critical catenoid. So if you take the critical catenoid, you take, say, its parameterization on R2 on a complete strip, you just wrap that around. So that's what we think of being as analogous to the cylinder. And the other singular limit, the necklace of spheres for the Delaunay surface, we think of as being replaced with sort of a necklace of disks. So at least in the intrinsic case, you have just a strip that would correspond to the critical catenoid. And if you imagine sort of pinching the strip in certain places periodically until in the limit you get just a bunch of disks, and on n, that's sort of the intrinsic picture we have in mind, that a singular limit for this moduli space should consist of disks sort of stacked on each other and with very singular points along the diameters. An obvious wrench that gets thrown in with making an analogy like this is that for the Delaunay surfaces, you can assert an ambient rotational symmetry, whereas for free boundary strips, this is not possible in general, except at the special value for the covering of the critical catenoid. And so the best one can do is try to assert some discrete symmetry. And so this is what we do. This is a way to interpret what Nikos and I have done, is that we construct examples near this singular necklace of disks by a gluing construction, which geometrically interpreted in the extrinsic geometry, we think of it as doubling the equatorial half disk, or n equatorial half disk. So now I'd like to discuss the geometry of this construction. But before getting there, I'd like to discuss the disk itself and how you can think about perturbing the disk as a free boundary minimal surface. So I want to discuss basically the blow-up picture. So if you start with the disk, equatorial disk in the 3-ball, or any equatorial disk in the 3-ball, you can study the linearized minimal surface equation, or the linearized free boundary minimal surface equation on this disk, which if you write it down, you get harmonic functions on the disk, and then the free boundary angle condition, if you perturb, the linearized version of this is this Robin boundary condition on the boundary. So the normal derivative is equal to function on the boundary. So I call a function that satisfies this boundary value problem a Jacobi function on the disk. Such functions are related to infinitesimal directions in which you could perturb in the linearized way the disk as a free boundary minimal surface. So if we're interested in constructing free boundary minimal surfaces that are in appropriate sense close to the disk, we would like to understand this problem. So more than this, we'd like to understand solutions that have singularities at 2 points along a diameter, sort of point P and its opposite point, because as I mentioned before, we're interested in a blow-up limit where we have this necklace of disks. And so the necklace of disks, they meet along points, diameter points. And so we expect singular behavior there, and the Green's function singularity in 2 dimensions is logarithmic. So we would like to look for solutions with singularities there. And we'd also like to assert reasonable symmetry, discrete symmetry. So we'd like to assert a reflection symmetry through a diameter orthogonal to the pair of points we pick, and then reflection symmetry through the line joining those 2 points. And so you can look for solutions to this boundary value problem that have these properties. And if you try hard enough, you can actually find an explicit solution. So you can, if you check, this does satisfy this boundary value problem. It has reflection symmetries through here, here, and then it has logarithmic singularities at these 2 points. If I identify this unit disk with the unit disk in the complex plane with a standard complex coordinate z, and then this point P I think of as, you know, the real number 1 or 1, 0 in Cartesian coordinates. So that's a place to start. And now I would like to talk about moving from this linearized picture on the disk to actually constructing a fundamental piece or fundamental domain for a free boundary minimal annulus. So this picture requires some interpretation. So I'd like to spend a couple minutes talking about this picture and adding to this picture. So now I'm switching gears, and this cartoon picture is of the 3-ball. And in profile, I have put the 2-dimensional disk, or rather half of the 2-dimensional disk. So this segment here is half of the disk I had in the previous slide, and the half I choose to call D+. So it's the half that has P, and the half that has minus P is not relevant at the moment. So this is in profile, the picture I had from before. And I'd like to slowly describe the symmetries of the extrinsic surfaces that we construct and how we construct them. So what we do is the surfaces that we construct depend on a small positive parameter var pi, and geometrically var pi corresponds to taking a small angle in the plane, the vertical plane that's orthogonal to the plane containing the disk. So I take that plane orthogonal, which is dotted here, and take another plane that's inclined at angle var pi from that plane. So I take that vertical plane, I tilt it by var pi, and I choose to call that plane P prime var pi. So I take that plane, and what I would like to do is I would like to construct a fundamental patch, basically a free boundary minimal disk that is mostly graphical over this D+. And what I would like to do is I would like it to meet this inclined plane orthogonally. So I'd like to meet that inclined plane orthogonally. The patch that I'd like to put should have the symmetries from the previous slide. In the plane of the disk, it should have this symmetry plane, which in the next picture you can't see. And furthermore, I would like it to also be symmetric with respect to the plane of the disk. So reflection through the plane containing the disk. So I'm now going to attempt to draw in profile a cartoon picture of how this surface might look. So roughly speaking, this surface would be described by the graph of an appropriate shrunk version, multiplied by a small constant version of this function in the plane orthogonal to P prime of omega. So there's a plane like that here. And I draw this just as a straight line segment in that plane, but it would have some deviation governed by the shape of that function g in the previous slide. And before I get to the boundary here, remember there was a logarithmic singularity in that function g from the previous slide. So if I follow this along to the singular point here, there would be a huge logarithmic singularity, and it would go down, and I'm not going to draw that. But before you get there, you stop following the function g, or the multiplied by small number function of g, and then you transition to a catenoidal graph, a piece of Euclidean catenoid, whose waist is centered at the point P. And so you place a small catenoid at P, and then it moves up because it has logarithmic growth. And then as it moves up, you want its logarithmic logarithmic growth to match the logarithmic growth or decay of the shrunk function g from the previous slide, where the g is, as I mentioned before, viewed as being in this plane, this tilted plane. And so the upshot is that if you do this, you would have a fundamental disk-like piece in this wedge-shaped domain bounded by p prime of omega and the plane containing this d. And if you do this in the right way, it will meet p prime omega orthogonally, and then it will also meet the plane of d plus orthogonally. Once you do that, you can then reflect this fundamental patch through this plane, through the plane containing d. And in this cartoon picture I don't have those reflected pieces, but I ask you to imagine them here. So just reflect this thing through here, you would get something like that. Reflect through here, you would get something like that. And then you can do repeated reflections. And as you do repeated reflections, the whole picture slowly precesses around the ball because this angle var pi is quite small. So I would like now to, I'm going to write some more analytical expressions explaining the same progression on the next slide with no pictures. But if there are any questions, now would be a good time. I could also put up Mario's picture again, which might suggest a more pleasant version of this if people prefer. Okay, so let me describe in words more and some more formulas the progression. So we construct a one parameter family of immersions that are governed by a small parameter var pi, which is the angle I mentioned before. And so in the plane, above the plane of the half disk, you think of the little patch that you construct as the graph of a function that here I call var phi, which is a sort of damped version of the function g, the Green's function from the previous slide, multiplied by a small number tau. And then you also add this function, which is just a linear function that has growth at p. So this is really just telling you that you're going up. If you choose to think of the thing as a graph over the disk, you have the Green's function, but then you have growth going up. And so this was a solution of the Jacobi equation over the disk, and this linear function is also a solution of the Jacobi equation over the disk. And together they have a bunch of symmetries. So this tells you how you think of the patch away from the point P. Near the point P, obviously you don't actually want a logarithmic singularity, but you want to transition to something that behaves logarithmically, namely a Euclidean catenoid. And the Euclidean catenoid that you'd like to choose is a catenoid whose size, and when I say size, I mean the radius of the waist of the catenoid. So if you take the center, the axis of the catenoid, and you go out until you hit for the first time the actual catenoid, I call that number here, this radius tau. So if you think of the catenoid as a graph over its reflection symmetry plane, you can write this out specifically. And here you can see the dominant term. This is sort of a junk term for large R. The dominant term is logarithmic. And so it's described via this behavior. And you can try to match the logarithmic growth of the catenoid, including its size, with the logarithmic decay or growth of this Green's function. And if you do that, you can relate the parameter tau, which you get to choose, and you hope or expect to be very small, in terms of the parameter var pi that is the basis of your construction. And if you do some calculations, you find that up to smaller factors, which I'm not writing here, that are basically error terms, that the tau should be chosen in this way. So if you this term is not very important. If you consult briefly this formula, if var pi is very small, then this tau is very small. Okay, so that's the basic setup. And so if you do glue things together in this way, you can do the gluing such that, so in the vicinity of point P, you have an actual catenoid that meets this plane orthogonally. So basically for free, by construction, you can reflect the surface across the plane of D plus smoothly. You have some issues here about reflecting the plane by P prime of var pi, but everything has been cooked such that to first order, essentially, you can reflect, and by smoothing things out, you can reflect smoothly across. And so this shows that you can construct a patch that's approximately minimal to first order, free boundary minimal to first order, and then you can smoothly reflect across this plane or the P prime var pi plane. And so if you do the subsequent repeated reflections, you keep reflecting, and then you will either reflect forever if var pi divided by pi is irrational, or if var pi divided by pi is a rational number, then eventually, as you keep reflecting these patches, these fundamental patches, eventually you'll close up. And then when you close up, the immersion that you get actually covers an annulus, because of course you could keep reflecting, but then you would just be repeating. And so the goal then is to do two things. One, choose var pi to be a rational multiple of pi, and then two, show that in this construction that you can actually truly make the fundamental patches free boundary minimal, make them both minimal surfaces, and then meet the boundary of the ball orthogonally. Let me just check how we're doing on time. Okay, so I have some more time. So the perturbation argument, so that you can actually achieve free boundary minimality, can be done and follows along similar lines to things that Kapouleas and I have worked on before. So I'll mention that in just a moment. But the important step on getting there is to show that when you construct initial surfaces, as I indicated previously, that the mean curvature and the contact angle are small in a quantitative way in terms of the parameter that's governing everything, the var pi. So the expectation is that as var pi shrinks to zero, the geometric objects involved become better and better behaved, and the geometry improves in appropriate weighted Holder norms, so that you get very good estimates on the mean curvature and contact angle. In essence, they should be basically in the appropriate norm, like var pi to 1 plus some power. So it's better than linear in var pi. And then the expectation, what we show is that for all sufficiently small var pi, independent of whether var pi is a rational multiple of 2 pi, each initial patch can then be perturbed to exact free boundary minimality by a perturbation fixed point argument. So this is what we prove. And then, of course, if you do take var pi over pi to be rational, the free boundary annuli that you get, since var pi is very small, they precess around very slowly, so it takes a long time for them to close up. So since the geometry of a fundamental patch is very predictable, its area is nearly half of the area of the disk. The area of one of these annuli is very large. And as var pi goes to zero, the area of these surfaces tends to infinity. And then correspondingly, the first Steklov eigenvalue tends to zero. So the behavior is, so here's again Mario's picture from before. Maybe we can study the picture briefly in light of what I mentioned. So unlike the embedded case, you can sort of asymptotically fill out the entire ball. So maybe it's worth just trying to concentrate on a little bit here. So if we concentrate on a little piece here, you can sort of see something that's close to a half catenoidal neck here, and then transitioning to two pieces that are approximately half disk-like. of course, as the degree of symmetry gets higher and higher, you of course converge to things that are much closer, truly look more catenoidal and disk-like. But then the problem is that since it's immersed, it's harder and harder to see a fundamental patch. But you can clearly see some of the symmetry planes here. There's an up-down symmetry through the z=0 plane here, and then symmetry through a plane here, and then you can begin to see the planes processing as you move through. I have a couple more minutes, so I'd like to mention just a couple final remarks about the methodology here. So what we did in this construction was a special case of a general methodology that in work with Kapouleas, and Kapouleas had started prior to working with me on what we call doubling constructions for minimal surfaces. So in these constructions, the philosophy is that one can take a minimal surface sigma embedded or immersed in a three-manifold and construct infinitely many embedded or immersed minimal surfaces that converge in the varifold sense to two copies of sigma. And then one does this by considering singular solutions of the appropriate linearized equation, and then basically replacing the singularities with catenoidal bridges, small catenoidal bridges. And so putting bridges in the vicinity of the singularities, and then far from the singularities, replacing the surface itself with a bigraph over the surface of the singular solution. So like we did here. And so in some of our recent work, we have developed a general apparatus for doing such constructions, and we've showed that we can apply successfully the apparatus to construct, for example, doublings of the critical catenoid as free boundary minimal surfaces in a three-ball, doublings of the equatorial sphere as embedded minimal surfaces in a three-sphere, doublings of the catenoid in R3 as complete embedded minimal surfaces in R3 of finite total curvature, doublings of the sphere as the shrinking sphere as a mean curvature flow self-shrinker, and the list goes on. So far, we've been able to successfully apply the apparatus when the ambient space and the sigma that you have has some discrete or continuous symmetries. But the PDE apparatus, once one has the appropriate families of singular solutions of the linearized equation, we can go from that to solving the nonlinear problem. So basically what we've done in general is reduce the nonlinear problem to the linear problem. And finding the appropriate linearized solutions is still a challenging problem in general. One other thing we've done is for those objects and for this particular application, we can derive expansions for the areas of these doublings. And so if you call M a doubling and L is the finite set of centers of the bridges or singularities of the linearized solutions. So as you of course expect, the trivial term in the expansion is that your doubling has twice the area of your sigma, but then you lose areas. The next non-trivial term is captured by what I've just highlighted here. So you lose pi times the sum of the tau p squares, where tau p is the size of the catenoidal bridge you place at p. So for different p's, you have different tau p's. Then you have higher order error terms. So this formula that we've derived at least shows that if you have a doubling with very small catenoidal bridges, that the area of the doubling is less than twice the area of the base surface. So let me stop here. I think that's all I wanted to say.
Thank you very much for the great talk. So if anyone has questions, you're welcome to unmute yourself, raise your hands, ask in the chat, whichever you prefer.
So I have a question already, sure. And I mean you briefly touched on this by saying that there is a perturbation to actual free boundary minimality argument. which is the part in every single one of those papers that's always confused me the most. How do you do that?
Yes, yeah. So I deliberately said little about that because I didn't want to bring in a whole lot more notation, which always takes a lot of time to explain. But
Sure.
No,
it
no,
could
I'd
be
be happy
heuristic as well. I don't think I even understand the heuristic.
Yeah, I'd be happy to explain more. So in essence, the heuristic is that you're trying to do an elaborate Newton's method argument, basically. So the initial surface that I qualitatively described here, or somewhat quantitatively described, is basically your first guess. So you try to construct something that's approximately minimal, where approximately means that you can estimate the mean curvature, and in this construction also the boundary angle. And you have to construct that by using basically your best guess for the linearized equation. So you have to start with, on at least one of the objects you have the disk, what is the linearized minimal surface equation? So if you were to perturb at the linear level, perturb to minimality, how would you do it? You would have to have a solution of this equation. So we take a solution of this equation, and then most of the time use the graph of this equation. So away from P, you're constructing to first order something that is minimal because you use a graph of this function G. Near P, you don't use that function because you want to put a small catenoidal bridge. The catenoid in R3 is minimal, and the half catenoid in the half plane is free boundary minimal in a half plane. And if it's very, very small, it will be, again, up to higher order error terms, free boundary minimal in this ball, because when you blow up, and the catenoid is very small, when you blow up the ball, it looks more and more like half plane. So you have two ingredients, each of which is to first order minimal or free boundary minimal. And then you need to make a good first guess, you need to glue them together in a way that you try to disturb those properties the least. And in order to do that, what you need to do is basically choose the geometry of this object and the geometry of this object well. And if you write down basically the appropriate expansions, you find the relation like this. So all of this is about, at the linear level, finding a good guess. When you go to the nonlinear level, you have to deal with nonlinear terms. And so when you want to perturb, so what you want to do is you want to start with one of these initial surfaces, and you want to do a perturbation, take a normal graph over one of these objects and perturb it to actual minimality. So you would like to solve the Jacobi equation over one of these initial surfaces and solve with error terms, because you'd like to kill the error mean curvature that you're supporting on one of these surfaces. So there's a lot of hard work that I did not in this talk discuss at all that goes into actually writing down the linearized minimal surface equation over this surface, showing that you can solve it with error terms. This is challenging because this initial surface has pieces with two different geometries. You have sort of this part, which looks a lot like a disk, and this part, which looks a lot like a tiny catenoid. So when you solve, you have to solve in some weighted holder spaces, because the geometry of the small catenoid is changing because it has extremely high curvature near P. So you would like to do that and then solve the linearized equation over this thing with error estimates. And if you've done everything well, you estimate the mean curvature on this thing in those weighted holder spaces, and then show that you can try to iterate away the mean curvature by perturbing using the solution operator that you construct with all of the weights everywhere. And then ideally you would like to get an iteration going that shows that you could converge to something that's free boundary minimal, but in practice, we use something like a fixed point theorem, the Schauder fixed point theorem, to show that there exists a perturbation that gets you to minimality. So in many of the constructions we've done before, we've worked out some of these issues sort of in general, so that this paper that I mentioned here, which will appear in the Cambridge Journal,
Mhm.
we sort of automated a lot of the last part that I just discussed now, but didn't discuss during the talk, the kind of progression from the linear objects, the nonlinear objects. And we showed that with appropriate linear objects, with the appropriate solutions of the linearized equation, we can always do those last steps. And then we can just do them. So the idea is that you try to reduce to the linear theory. Of course, in this particular application with this free boundary disks, the setting was different enough that we couldn't just quote the other paper because we had the free boundary, and then we had this additional feature that things keep bending around. So that was a little bit unusual. I don't know if that helped answer you.
Yeah.
Okay, so did someone else have a question for the speaker?
Can I ask a question as well?
Yeah.
Hey, Peter.
Yeah, make sure.
I wanted to ask about so you mentioned the first eigenvalue goes to 0 necessarily. And we also know that any free boundary minimal surface is critical point for some Steklov eigenvalue. So is it hard to compute here? Which eigenvalue would that be?
That's a good question. I do not know. We have not tried. That's a very interesting and natural direction to think about. We have not actually tried to do that carefully. So I don't know the answer to that question. I mean, I had idly, before we embarked upon this construction, but after we had the heuristic picture for how these things should look, I had idly wondered about that, but I've never seriously tried to work that out. So that's an interesting question.
It'd be curious to see. So there's a natural sort of conjecture for the upper bound for the kth eigenvalue on the Steklov, right? When you take the Catenoid and you add a bunch of disks to it.
I see.
Somehow your construction suggests that in the limit you get just a bunch of disks, right? So somehow it might be close to being optimal in some sense, right? So it's not quite Catenoid plus disks, but a bunch of disks for large number of disks is almost like a Catenoid plus a bunch of disks.
I see. Yeah.
I think it would be curious if it's in some sense almost optimal.
Okay, thank you, Misha. Is there anyone else who would like to?
Yeah, just to follow up on one last comment about Misha's question. Yeah, it might be possible using similar. I mean, to get an expansion like this, we just had to understand, the ingredients of the objects well enough, and one might hope that one could do a similar thing, asymptotic expansion for the first eigenvalue in a similar way.
Okay, well, thank you. Well, we can still keep on chatting if we want to anyway, but in any case, we'll meet again next week with the talk by Maxime Portier-Bourg. And thank you, everyone. Thank you.
Thanks a lot, Peter, for the talk.
Thank you. Nice to meet you.
Yeah, nice to meet you as well. So you're in North Carolina now, right?
That's correct. Yes, I'm at North Carolina State University in Raleigh.
Okay. The basically only city I know in North Carolina.
Oh,
only because that's a city where there's a hockey team, which is my main reason for knowing.
Oh, I see. Okay, yeah. On one of the buildings downtown, they've taken half of the building. They have a huge advertisement for the hockey league or championship or something like that.
Have you been there for a while?
This is my third year, so I've been here 2.5 years. So
okay.
A little, yeah, it's been great so far.
All right. I have to go for now, but I hope we get to meet in person next time instead of.
Yes, that would be nice. That would be nice. I should probably, unless other people have questions or want to say anything, I should probably go myself because I would like to eat lunch sometime.
I think most people have left, so
Okay, thank you, and nice to meet you. And thanks again for the invitation.